So in the last class, we introduced a new special type of subring called ideal. The definition of the ideal is this. Let n be a subring of a ring R such that an is contained in n and nb is contained in n for all a comma b in R. Then n is called an ideal. And the reason for defining a special subring like this is because we can construct a factor ring from here. If n is an ideal, then R by n, that is the collection of left or right cosets, forms a ring called factor ring R by n with the following addition and multiplication. Addition is n plus a plus n plus b is equal to n plus a plus b. N plus a times n plus b is equal to n plus a. So that is the reason we come up with a special kind of subring. This is actually similar to the subgroup of a group. Sorry, normal subgroup of a group. Examples. Z is a ring and MC is an ideal of Z. That is because for any n in C, NMC is contained in MC. And that is exactly what this means. Of course, this is a commutative ring, so the other portion is also valid. So this is one example of an ideal. In group theory, we know that there exists a homomorphism from a group to its factor group. So group theory, groups, let H be a normal subgroup of G. Then there exists a homomorphism psi from G to G over H defined by gamma of A is equal to H plus A or is equal to A plus H. So this is a group homomorphism. Now, if you come to rings, let us see whether the same definition holds good for a ring also. So let N be an ideal of a ring R, then define gamma from R to R by N by gamma of R is equal to N plus R is equal to R plus N. Then gamma is a group homomorphism. Now let us see whether we can extend this one to a ring homomorphism. So what we will do is, let R1 comma R2 belongs to R. So gamma of R1 R2 is equal to, by definition, is N plus R1 R2, and by the definition of multiplication, this is actually R1 times N plus R2, and that is equal to gamma of R1 times gamma of R2. So the definition of group homomorphism is true for a ring homomorphism also. So gamma is a ring homomorphism. So the result is, if N is a ideal of R, then there exists a ring homomorphism gamma from R to R by N, defined by gamma of R is equal to N plus R is equal to R plus N. This is a ring homomorphism. So let us see whether the fundamental theorem on homomorphism holds good for rings also. The fundamental theorem on group homomorphism. So let phi be a group homomorphism from G to G prime, and H be the kernel of phi. Then we have G to G prime, that is phi, and we have a gamma here which goes from G to GH. Okay, then there exists a mu defined by mu of an element from here will be A plus H, and that A is from G, and that is equal to phi of A. Actually, this is actually from phi of G. G will be somewhere here. G prime will be somewhere here. The same theorem holds good for ring homomorphism also, because this is a ring homomorphism, this is a ring homomorphism, and our definition is not going to be changed. So in rings, so fundamental theorem on ring homomorphism follows from the corresponding theorem in groups. That is, if N is a if phi is a ring homomorphism from R to R with kernel n, then R to R prime is phi, and here there will be an R over n. We already established this one. There is a ring homomorphism, and the definition of phi and R are exactly same as in groups. So this map holds good. This is going to be mu. So mu of R plus n is equal to phi of R for all R in. Now let us do some problems using homomorphisms, factor groups and ideals. Ring homomorphisms. So the first problem what we are going to do is, let f is equal to f from R to R, where R is the set of real numbers. Then f is a ring. Now take a collection of some special functions here. Let n is equal to the collection of all f in f such that f of a is equal to 0 for some fixed a in R, which means that if you draw the line here, this is our any of the f of f1, f2, etc. So this is our a. So all the functions have to pass through this a0. So that is this. So verify if n is a ideal. So first thing what we need to do is, we need to find out, steps are actually verify if n is a subgroup of R with the function addition. I am going to leave it to you as an exercise. And it is actually a subgroup. N is a subgroup. Things we need to prove is identity belongs to n, inverse axis, and n is closed under addition. So I am not going to prove this one, that I am going to leave it to an exercise. I am assuming that n is a subgroup. Now we need to show that it is a subring. If you fails here, then you don't need to worry about it. It's not an ideal. So next step is verify if n is a subring. And how do you verify? All we need to do is to show that n is closed under multiplication, because the associativity and distributive law follows from R. This can be easily proved that it is closed under multiplication. So let f1 comma f2 belongs to n, and that implies f1 of a is equal to f2 of a is equal to 0. So f1 times f2 of a is equal to f1 of a times f2 of a, and that is equal to 0, implies f1 times f2 belongs to n, and that implies n is a subring. N is a subring. So n is a subring. Now we have to show that it's an ideal or not. So how do you prove it's an ideal? So let G belongs to F. So we need to show that G of n is contained in n and Ng is contained in n. This is what we want to show. So let F belongs to n. So G times F of A is equal to G of A times F of A. This is not equal to 0. Not necessarily this need not be 0, but this is 0. So this means G of A times 0 equal to 0, and that implies G times F belongs to n, and that implies Gn is contained in n. Similarly, Ng is contained in n, and that implies n is a ideal. Now let us find out the different homomorphisms from Z cross Z to Z cross Z. So find all ring homomorphism from Z cross Z to Z cross Z. So define homomorphisms using generators of Z cross Z. That means you need to define phi from Z cross Z to Z cross Z by defining phi of 1, 0 and phi of 0, 1. So let phi of 0, 1 or 1, 0 is equal to mn. This is a general element in here. So this implies phi of 1, 0 times phi of 1, 0 is equal to m, n times m, n, and that is equal to m square n square. And this is phi of 1, 0 times phi of 1, 0 is again phi of 1, 0, because if you multiply these, this is going to be 1 and 0, and that is equal to m, n, and that implies m square is equal to m and n square is equal to n. So the possible values of m and n are 0 and 1. Similarly, this is actually the image of phi of 0, 1. So phi of 0, 1 can be Mn where Mn n's are 0 and 1. Similarly, phi of 0, 1 is equal to Mn where M and N are either 0 or 1. Now, if you compute phi of 1 comma 0 times phi of 0 comma 1, what is this? This is actually equal to phi of 0 comma 0, and that should be 0 0, because this is the additive identity. The additive identity of the image of additive identity will be the additive identity of the range where it is going to. So let us take when phi of 1 0 equals 0 0, then phi of 0 1, see this, if you want to make a definition of a homomorphism, you have to define both. So when this is equal to 0 0, this can be either 0 0 or 1 0 or 0 1 or 1 1, because if you multiply, this will be all zeros because this is 0. But when phi of 1 0 is equal to 1 0, then phi of 0 1 should be, one value is 0 0, the other value will be 0 1. That's all, because you cannot take 1 1. If you take 1 1, when you multiply this one, you will get a non-zero value, which is not the one which you want. And 0 1 also is not possible. 1 0 is also not possible. So these are the only two values when 1 0 is mapped to 1 0. When 1 0 is mapped to 0 1, then phi of 0 1 should be 0 0 or 1 0. So that if you multiply these two, you get the 0 value. When phi of 1 0 is equal to 1 1, then phi of 0 1 should be 0 0. So these are the only possible values. So 1, 2, 3, 4, 5, 6, 7, 8, 9. So there are only 9 ring homomorphisms from Z cross Z to Z cross. Let us find out the ideals and the factor rings of C12. Find all ideals and factor rings of Z12. Z12 is actually a ring, right, with addition as addition modulo 12, and multiplication is multiplication modulo 12. So in order to find the ideals of this, those ideals are subrings such that AN is contained in N and NA and B is contained in N. And subrings are subgroups closed under multiplication. So the subgroups of C12 are 1, 2, 3, 4 and 6. Actually 1 will be Z12, 2 will be 0, 2, 4, 6, 8, 10. The subgroup generated by 3 is 0, 3, 6, 9. Subgroup generated by 4 is equal to 0, 4, 8. And subgroup generated by 6 is going to be 0, 6. These are the only subgroups. So first we need to, first you already have all the subgroups. We need to see that whether it is a subring. Verify if these subgroups are closed under multiplication. The answer is yes, it is closed under multiplication. If you take any of this, let us say if you take the subgroup generated by 3, if you multiply any two elements, you will get the same element here. 3 times 6 is 18. 18 is actually 6. 18 mod 12 is 6. So this is inside this within this subgroup. So all these are subrings. Now we need to verify if these subrings are ideals, and all of them are ideals. For example, if you take Z3 times any number, let us take 2, and that is equal to 2 times 0, 0, 2 times 3 is 6, 2 times 6 is 12, and 2 times 9 is 18. So that is actually 0, 6, and which is contained in 0. And that is exactly what this means. So all these subrings are ideals. Now if you want to compute the factor rings, let us compute one factor ring. Compute Z12 over 3, and that is equal to 3 plus 1, 3 plus 2, and 3 plus 3. This is 12, 1, 2, 3, 4. No, this is only up to this. These are the only possible values. So this is the factor ring. Actually this is a factor group and factor ring, both are same, elements are same. Okay.